Have you ever wondered how it's possible that we can have a satellite orbiting the Earth, like how that actually works? Because I find that quite fascinating to have such a small thing being able to move in a circular path around its Earth itself. And it's exactly what I'm going to talk about in this video. I'll read the actual document. It says, define the terms orbital velocity and the quantitative and qualitative relationship between orbital velocity, the gravitational constant, mass of the central body, mass of the satellite, and the radius of the orbit using Kepler's law of periods. There's two things we have to do. First, we have to define the terms orbital velocity, which I'll do in a second. And then we have to talk about the relationship between orbital velocity, gravitational constant, mass of the central body, and mass of the satellite, and the radius of the orbit using the Kepler's law of periods. And it says quantitatively and qualitatively. So qualitatively means I have to describe, and quantitatively means just give example with numbers. So first we'll talk about orbital velocity. And as the name would suggest, we've got orbital, so how fast it goes around its orbit. And that's more or less what it is. So orbital velocity is just the speed, the instantaneous direction and speed, because it's a vector, it has direction and speed. So the instantaneous direction and speed of an object along its circular path. So if you have a ball on a string, it's saying how fast is it moving per second. Instantaneous means we'll do it per second. Now, the example would be, okay, if you have, let's say, a radius of 2 meters, again, this might be a ball example, so the radius here would be 2 meters, and the time it takes for it to make one whole lap, one whole path from here to here, so just 360, takes 0.1 seconds. Now, if you have, this is the actual calculation you have to do. This is how you get orbital velocity. Orbital velocity, v, equals 2 times pi times r, which is radius, divided by t, which is the periods, which is how fast, or how long it takes for it to make one complete circle. So if we put that into our calculator, we would have 2 times pi, which is 3.14, times 2, so it's 2 times pi times r, and r is 2 as well, times 2. And then you divide that by the time it takes for one period, which is 0.1. And that gives you so in this case, the ball is moving at a speed of 125.6 meters per second. And that makes sense because the faster, so this is how long it takes for it to make one complete circle. And the smaller that number is, the faster it would be going. Because now it takes 0.1 seconds to make a complete circle. If this were 0.0001 seconds, then this number would be higher. The reason why is because it would be going at a crazy path. It would make hundreds of thousands of spins per second if it were that smaller, if it were even much smaller than this. So the smaller the period here, the faster it's going. And that makes sense because that's the time it takes to make one lap. So yeah, the orbital velocity, that was the instantaneous direction and speed of an object moving along its circular path. That's the first part. We define the term orbital velocity. Now we have to talk about the next part. We have to talk about the relationship and Kepler's law. Now this here is Kepler's law. R divided by the period squared equals gravitational constant times the mass of the Earth divided by 4 times pi squared. That's your actual Kepler's law. Now, if we put in our velocity, which we got, this was the orbital velocity, calculation for the orbital velocity, because what we have to talk about orbital, like the relationship between orbital velocity, gravitational constant, mass of the central body, mass of the satellite, and radius of the orbit. We have all of this stuff here, most of it, except for we don't have velocity yet. But we have to talk about velocity. So what we can do is we can actually put velocity in for t. We can substitute it in, because you can see here, if we rearrange it, which I'll do in a second, I'll show you what happens if we rearrange it. But if we rearrange it, then we get, so if we put t on this side equals this divided by, now I've just rearranged it. So now I've just rearranged it. And now what we can do is we can substitute t in for this, which means that t equals this here. So what you see in a second is, now this is the same formula here, except for instead of having t, which we had beforehand. We have this here, which was we established by rearranging it. It's the same as t. And we have that square here because it was t squared. Right? But this is the same Kepler's law, just with having t substituted in, so we can have our orbital velocity in our actual equation. Now if we rearrange it some more, I'm going to spare you how I did that because it will take a bit too much time. But now if we rearrange that more, we will cancel things out and we'll have this left. This is what we have left over. So leftover. And this is still Kepler's law. And we use Kepler's law to find out how fast things are moving around Earth itself, for example. Because remember, G was the gravitational constant. M was the mass of the Earth. And R was the radius it was away. So whatever we're talking about the satellite, how far it was away from the Earth itself. And I'm going to go and give an example of this, but I'm going to show you the relationship between this because that's what we have to do in the dot point itself, to show relationships. Alright, so if I, for example, were to tell you, okay, calculate velocity if the satellite is an altitude of 500 kilometers. What that means is our satellite is here. This is our satellite, this dot here. And it has an altitude of 500 kilometers, which means this part here is that radius of that is 500 kilometers. But we need to have the overall radius. And when we talk about radius when it comes to satellites, what we have to do is we have to actually take the radius of the Earth itself and add that to the radius of the satellite. So this is the radius of the Earth, here, from here to here, and then add that to the radius of the altitude, which makes sense because we want to have the complete radius between the actual middle of the Earth and the satellite. And if we just take the altitude, that's not enough. We need to take the complete, which means we take the radius of the Earth plus the altitude, and that gives you your complete radius. So if we take that same formula and just change it a tiny bit, and we would have it as so. We would say, okay, well, Earth's radius, ER, that's Earth's radius, plus the altitude, so the altitude. That together is our overall radius. Because of the reason I've just established beforehand. The actual radius is so from the middle of the Earth to the point where we have our satellite, which is both of them combined. So now if we put numbers in, so we want to have V, so this is what we're looking for. And we know that usually gravitational constant stays the same. So this is always given. This is given. We have our mass of the Earth, which is usually also always given. So the mass of the Earth is given as well. As is the radius of the Earth, because these are constant, they're always the same, so they're usually always given. So all we have given here in the actual question is the altitude, which is 500 kilometers, but the rest we usually have in our booklets. So all we have to do is we have to substitute the numbers in. So we would have to say, okay, well, that equals to 6 times 6, 7 times 10 to the power of minus 11. That was a gravitational constant. So this was G. Times, and then for the mass of the Earth, 5 times 9, 7 times 10 to the power of 24. That was the mass of the Earth. So we've times them together. And divide that by the combination of the radius of the Earth, which was here, 6.38 times 10 to the power of 6 meters. And then we have to still add, so we don't times it here, we add, plus the altitude, which is 5,000 kilometers. And 5,000 kilometers is the same in terms of meters, so 5,000 kilometers is 5,000 times 500 times 1,000. That's 500 kilometers in meters. Right, so this would actually get your results. I can't do it because my calculator would take way too long to do that. But if you were to put that into your actual calculator, you will get the result. But we have to talk about the relationships. We have to talk about the relationship between the orbital velocity, gravitational constant, mass of the central body, mass of the satellite, and the radius of the orbit using. So we'll talk about the gravitational constant first and the mass. So the bigger the mass, because it's on top, here we're timesing it, the bigger the mass, the bigger the velocity. Which makes sense because mass is gravity. So mass determines how much gravity we have. And gravity is the centripetal force. The force which pulls this actual satellite in is gravity, which means the more gravity you have, the faster it will be moving because there's more force, right? So the more mass we have, the higher our velocity, because mass is directly related to the gravity itself. Now also, the higher that gravitational constant, the more velocity would it have. But the gravitational constant, because the constant is always constant, so it doesn't really matter. It's always going to be the same. Now also says we have to talk about the mass of the satellite. I can tell you the mass of the satellite because it's so small compared to the Earth itself. The Earth is 5.97 times 10 to the power of 24. That's a huge number, and the Earth itself is tiny in comparison. The satellite is tiny in comparison, so we can actually ignore the mass of the satellite. It's not important. We need to just care about the mass of the central body, which was the Earth itself. That was this here, central body. We need to care about the gravitational constant, but that's always kept the same. And the bigger the radius, so the bigger the radius, which is here, so the bigger here, the smaller the velocity. Which makes sense, because if, for example, if we have it out here, let's say our orbit is around here, then the distance between the Earth and the actual satellite would be much bigger, and that would mean the gravity is smaller, because the actual gravity is related to the distance, the radius. So this here would be experiencing less gravity. Less gravity, which means less force. And if there's less force, then there's less acceleration as well, less velocity. So the more mass you have, the faster it will move. The more radius you have, the further is away from the Earth itself, the slower it will move in a circular path. G is always constant. That's also what asked you in the gravitational constant, but it's always constant. And the mass of the satellite itself is not important because it's so small in comparison to the mass of the Earth. And those are the things you need to be looking at. So those are the things you need to be comparing. And yeah, you should obviously hopefully have a sort of a conceptual understanding. But if you get those kind of numbers, you all have to do is put the numbers in the actual formula, which is this one here. And I showed you earlier how you derive that as well. And you should get your correct value. I hope that was useful.
Thank you for watching.